Okay, well, welcome to our second meeting of the day of the SIGHPC Education chapter. I'm Steve Gordon. I'm the current chair of the chapter. Helping me today will be Scott Lathrop. He'll be keeping track of questions. We're going to do a short presentation and then accumulate questions, which we'll answer at the end of the broadcast. And so bear with me while I get ready to share my screen and give a short presentation. So let me just start with some technology logistics. I already mentioned we're having the presentation followed by question and answer. You can use the question button from Hangouts on Air to pose a question at any time. And what we'll do is collect the questions throughout the talk, and then Scott will go through those at the end of the talk, and I will do my best to try to provide the answers to those questions. You should note that there are time delays between requests and replies because of the technology. The time between when I say something and when you receive it is somewhere between 30 and 45 seconds, depending on your network connection. So you can expect delays as well as you post a question until we see it on the screen. The entire session is recorded and is available on YouTube, and the slides that I'm presenting today are already posted on the chapter website, which I'll show you later on, but that website is sighpceducation.acm.org, and I'll show you some other things on that site later on. The purpose of today's meeting is to give an overview of academic programs in computational and data sciences as a way of giving a background as to the status of at least the academic part of computational science and education. So what I hope to do is to summarize the number and types of programs. I want to review with you some competencies that are embedded in a number of these programs, what students are supposed to learn from them. I'm going to provide some specific examples of different program types from institutions of different sizes and different types to give you an idea of the range of programs that are available. And then I'll spend a little bit of time at the end talking about issues with program implementation and maintenance. So the information sources for the programs themselves are we started with some lists that are provided by SIAM and others of computational science programs. It turned out that this list is not very up to date, so we did an internet search for programs and then some cursory analysis of program websites. And since the data come from the internet, we all know that they are reliable, which I'm of course saying tongue-in-cheek. So what I really want to say is that I'm sure we missed some things, and so we actually invite you to correct us if we're wrong. And we could be wrong in two ways. We probably left out some programs that exist because we couldn't find them, and also we may have listed some programs which continue to have a web presence but have actually disappeared and are no longer functional. The full listing of both the undergraduate and graduate programs are available on the HPC University website, and again I'll show you that later on, so you can go in and look at the full listing and explore the programs yourself after the meeting. Let's just start with some simple statistics. So we found 191 programs. The majority of those we found were domestic, although we did find quite a number of 51 foreign programs. I'm sure we missed a number of those because we're not aware of them. Not all of them are translated into English, and therefore we wouldn't know what computational science is in that language and so on. But it does show that there are a significant number and actually a growing number of programs in academic institutions. The split between graduate and undergraduate is as you see here, 157 graduate programs and 34 undergraduate programs. Let's talk now about some of the general characteristics of the undergraduate programs. We found that there are 12 programs that have majors in one or more aspects of computational science. So these are Bachelor of Science degrees. Some of them are tagged degrees, specializing in a particular area. Some are general, bachelors in computational science, but some might be named degrees like bachelors in computational engineering or something like that. They're typical undergraduate programs then that have a variety of requirements that are general education requirements for the undergraduates, and then a specific set of in major courses that are required, and some that are optional in order to get the degree. Most of the programs are minor programs. There's 20 of those. The mean number of undergraduate credit hours for those is 19, where 18 is actually the most typical number, but they vary in scope. So some of them have a minimum of 12 credit hours and some a maximum of 28 credit hours. They have a wide range of names, so not all of them are called computational science. So a rough indication of that is shown here. 2 were applied math kinds of programs. 2 were designated as bioinformatics or computational biology programs. 3 is computational physics. 2 is computational engineering. The majority of them, 11, were just more general interdisciplinary computational science programs, and that implies that they involve more than one academic domain, generally several of the physical sciences, biological sciences, computer science, and mathematics. 1 was labeled as computational thinking, and 3 is data sciences, and 1 is scientific computing. I should note that we probably have a vast undercount of data science curricula, probably because those are newer, they're a little harder to find, and we did not count data science programs that are focused on business. We only counted the ones that have an aspect that relates to to the sciences and engineering. We may later on try to compile a better list of data science programs and classify them as to their different foci, but we haven't done that so far. Now, all programs require some mix of computer science, mathematics, and 1 or more domain sciences. And the mix of those varies by program type and at each institution. But I thought it would be useful to review with you some competencies that were developed as part of several NSF grants with the community of people from a variety of disciplines, and those competencies can be used as a way of formulating a computational science program. So I'm going to go to this web page now, if you bear with me. So here's the HBC University homepage. You should be seeing that now. If I go under educators, there's a section called competencies. We've actually developed the competencies in 4 areas: undergraduate level computational science competencies, which I'm going to concentrate on mostly. We have some graduate level computational science competencies, and we also have 2 sets of data-driven science competencies, basic and advanced. If we look at the undergraduate competencies, you can see that the areas involved here are typical of many of the minor programs as well as the majors in terms of the kinds of skills that students acquire in these programs. When we put these together, it was with the idea that faculty are forming these programs at different universities, each of which has its own unique curriculum, and so it's hard to divide things into courses. The competencies then could be embedded in existing courses or in new courses, depending on what would work best at that particular institution. And what we tried to do is make these as specific as possible as sort of a guideline as to what should be covered. So it's a hierarchical framework. So if we look, for example, at the simulation and modeling, at the first level, we have a number of objectives of simulation and modeling skills that we would want students to have when they completed a program. And that starts with explaining the role of modeling in science and engineering, working through a number of other issues of creating a model, representing a model with various mathematical functions, understanding computer models, assessing them, verifying them, and then actually completing a model project as a sort of a capstone. Under each of these, we then have specific descriptors that that go with them to sort of guide the development of instructional materials. So if you look at this subsection under explaining the role of modeling in science and engineering, what we actually have students do is we give them a list of either science or industry projects that have been advanced because of modeling and simulation, and make them look for some of these things that were accomplished by doing modeling, whether that was getting something to market faster, improving the cost effectiveness of a design process, validating models with experimental results, and so on. So these can be guides to anyone that's creating a program as to what kinds of materials need to be covered. I won't go much deeper into these, but you can see that the major areas here, besides simulation and modeling, are programming and algorithms, a couple of mathematical subjects, differential equations, numerical methods, optimization techniques, parallel programming, and scientific visualizations. If we go back to the competencies and just do a quick look at the others, at the graduate level, what we've defined is at least two subsets of technical skills: intermediate level scientific computing and high performance scientific computing, both of which are necessary if one is going to do graduate research using high performance computing. And then finally, under the data-driven competencies, we tried to specify what skills are needed in statistics, data mining, data handling, data archiving, etc., that are part of the way that data-driven science is advancing. I'll leave you to go back and look at those competencies in detail on your own. If you have any questions or comments, please feel free to send them along. Let me talk a little bit about graduate programs. Most of these, about 20, are general programs, interdisciplinary programs in computational science or scientific computing, about 20 programs. The next highest number are in computational engineering, so that it doesn't necessarily encompass all of computational science, but focuses more on engineering techniques. And then beyond that, there's a wide range of other programs focusing on specific domains, things like bioinformatics or material science or data sciences or something else like that. It's not possible to sort of list all of them, but I'll refer you back to the list of programs to look at yourselves. Let's look at a few examples of different programs that I think are representative of the types you find, and ones that I know are, so these are not chosen at random, these are ones that I know about in a little bit of detail so that I could illustrate some different points. So I'm going to start with the minor program in computational science at Ohio State University. This is 18 credit hours. It has core courses which mimic some of the things in the competencies we just looked at: simulation and modeling class, programming and algorithms, numerical methods, and a capstone research or internship experience. Some important things to note here was that for some of the basic core courses, we had to give options. So for simulation and modeling, there are some places in the university that offer courses that meet these objectives. So there might be one or more courses in engineering, for example, that focus on modeling. But for some of the other sciences, there is no such introductory course, so we had to come to agreement on an introductory course that would be available to all students without a lot of prerequisites. And in this case, computer science agreed to teach such a course, which also overlapped with the programming and algorithms that taught a bit about programming while it really focused on modeling principles in the simulation and modeling area. Similarly, with programming and algorithms, we didn't want everybody to have to take the same courses that computer science majors take in programming if they're not computer science majors. And so again, there was a course developed for non-computer science majors that got at programming for those other majors, again, without a lot of prerequisites going into those. For numerical methods, there were a choice of several math and engineering courses, and the capstone research or internship experience meant that a student could either find a faculty member that was doing research using computational modeling and work with them on that research, often resulting in perhaps co-authorship on a research publication, but the experience is the most important thing, or they could get an internship with a private firm or one of the national labs or some other internship involving computational modeling. The other interesting thing about a large institution like OSU is that the elective courses across many disciplines, and some of them are not the typical ones that are the tradition in computational science. So you can see that there's courses in computer science, survey of artificial intelligence, bioinformatics, computational chemistry, a couple of different biological courses, a mathematical modeling of biological processes, and quantitative cell biology for engineers and scientists. But you see some non-traditional fields like computational linguistics, experimental economics, spatial simulation and modeling in GIS, and introduction to mathematical psychology. So a lot of these are things that wouldn't be available at every institution, but because of the size of Ohio State and the wide range of expertise of the faculty, these wide range of electives can be offered so that it would accommodate majors from many fields. I should also note that in some parts of the university, the major and minor courses can be overlapping, but it varies by college. So in engineering, some of the courses that are part of the major might also be part of the minor, so you don't have to take all 18 extra credit hours to get to the minor. Whereas in some of the arts and sciences areas, all the credits have to be unique. You can't count it both towards your major and towards your minor. And again, that varies from institution to institution. A second example I want to cover is is typical of a liberal arts college. This is a Capital University. This is 21 hours of credits. You can see a slightly different orientation, but overlapping with the previous example. The required courses, Introduction to Computer Science. You can take either calculus or a specialized calculus course for modeling in the biological sciences, and they did this because they found that their biology students were weaker in math and needed an applications-oriented course. Computational Science 1, which is really the modeling and simulation class, the differential equations and dynamical systems, numerical methods, and also a research experience. And their set of electives is narrower, reflecting the expertise of their faculty in just 5 areas and not the larger list like we saw in the Ohio State example. The last example I'll give is of a new data sciences minor, which is 23 credit hours at the University of Mary Washington in Virginia. And this has a different orientation, and so it focuses more on statistics and different kinds of mathematics and data mining. And so you can see the required courses include statistics, linear algebra, a computer science course, a data mining, and it does have a modeling and simulation course. And then the electives are either going deeper into the computer science part of data science with data structures and analytics application development, or a more statistics orientation in a course called Foundations and Applications of Data Analytics, and another a computer science course in parallel processing. So these sort of represent a range of things that are somewhat typical, although every program is unique. These are sort of give you a representative idea what the contents are of these undergraduate programs. So let me talk a little bit about program organization. It's difficult to tell the administrative arrangements from the website, so I couldn't do an actual count, but by observation and other experiences, I think I can divide these into two major groups. One is some sort of interdepartmental agreement to teach courses and share students in credit hours. So a lot of the computational science programs at both the undergraduate and graduate level involve making these arrangements between departments about who's going to teach various parts of the core courses, what the electives are, and so on. And that's very much like the program at the example programs I showed at Ohio State and Capital University. Another model is where there's a lead or dedicated department that controls core courses and relevant instructional resources, but still may have electives that range across the university. It's difficult to say which of these is advantageous or disadvantageous. Both of them have been successful and both of them have run into problems. As you might imagine, the interdepartmental agreements are sometimes hard to achieve on some campuses because there may be a department or two that doesn't want to participate, where there are no faculty that have computational science expertise, even though some of their students might be interested in the program. But in that case, problems may arise because the assignments for teaching loads, resources, and other things are decentralized and may cause problems over time. On the other hand, that would be an advantage of a lead department that has dedicated instructional resources, but there may be internal arguments about who should be the lead on campus, who gets those resources, and how the other departments then participate. So anyone familiar with academic programs knows that these are the possible fodder of huge academic wars, but hopefully, obviously in the case of the programs we've seen, they've been resolved to some degree. Whoops. Went too far. So some of the issues with these programs that I might bring up, one I already discussed, which is financial resources for interdisciplinary programs. Often at our institutions we have departmentally oriented budgets, and the domain courses take precedence over interdisciplinary things, but there are campuses that have successfully introduced interdisciplinary programs and given them separate funding lines, but this can be an issue in the stability of a program over time. A second issue that often arises is disciplinary course prerequisites. I mentioned a couple of those earlier on when I used the Ohio State example. So if you're going to take, a computational physics course, it might mean that you have to have already taken 2 or 3 other physics courses. That might work out, like if you were an engineering major, you might have had those physics courses, so you could then take computational physics, but if you were a major in chemistry, you might not have had those, and that can become a problem. And those things need to be examined as a program is put together to make sure that there's a clear pathway through a program, interdisciplinary program for all kinds of majors. The third one is an interesting one, and that is that since most of these programs, at least at the undergraduate level, require extra credit hours, there are many students that are not willing to do those extra credit hours, even though it might be sort of good for them. So I've had faculty who've told me that, yeah, their students recognize that if they took these extra 2 or 3 courses, they would learn a lot more, and they might even be better off on the job market, but they want to get through their program as quickly as possible. And so what tends to happen is you get a only a subset of students that probably should get this material as opposed to all the students that should get it. And that tends to constrain the size of these programs. And that's going to be a continuing problem until computational science is really integrated into the entire curriculum. And the final issue I want to bring up is one of marketing, even though once we're exhausted from putting together these interdisciplinary programs, our problem is marketing them to the students. This is not an easy task and not something that academics are very good at. First of all, computational science is something, particularly for undergraduate students, that they've never heard of before. So they need to be educated as to, what it is and what are the opportunities and what does this do for them in their careers. And that marketing might have to also go to their parents if they're undergraduates, paying for their education so that they understand why they're taking these extra courses. And that's, again, a continuing problem. And some campuses are better at this than others, and those that are better have better enrollments in their elective courses, and others may suffer as a result. So elements for success, based on my observations, nothing real scientific about this, but at least my observations from some existing programs. The programs that tend to be most successful have strong connections to ongoing research efforts at their institutions and or additional industrial partnerships. So if there's strong connections to research efforts, that means that there are faculty that are going to gain from doing the instructional part by having students that can make contributions to their research efforts, and that will strengthen those programs. There are also cases where there are industry partners that either provide funding for some part of the program or provide gateways to internships that help the program, or perhaps even more importantly, they provide information to the administrators at the university that might not know anything about computational science, about the demands for these skills in the market, so that resources flow from the university to make these programs happen. A second observation of success is you need a strong group of participating faculty across multiple disciplines. If it's only one emerging from one discipline or just two disciplines on campus, that's likely to be a weaker program. It's going to be harder to be successful. There aren't, if we look at the marketing problem, if they're not students from multiple disciplines, you may not hit the numbers you need to make a course happen, and so on. So the broader the range of participating faculty, the stronger the program. I already mentioned increasing private sector push for qualified employees as a way of convincing universities that they need to do something about this, and so anything we can do to find partners from industry to educate our administrators that this is an important thing to do, the better off our programs will be. Universities that have flexibility in their internal financial and appointment arrangements tend to be stronger. So some universities give more credit at promotion and tenure and raise time to interdisciplinary programs, whereas others are sort of stuck in disciplinary boundaries for making those decisions, which makes it harder for faculty to participate in interdisciplinary programs. So anything that relaxes those things will make for a stronger program. The final thing I want to mention is that is really a goal that I would like to see for our chapter, and perhaps push up to the ACM in general, and that is endorsing things like these competencies or these programs by professional societies, which would increase their visibility and potentially then their viability at the universities, and something that I want to engage in continuing discussion about with the chapter to see how we might implement this as time goes on. So I think we're almost to questions and discussion. Before I do that, I wanted to go back to the website and just show you a couple of things. So I mentioned that the programs themselves is, if we go under students, you can see that we have graduate programs and undergraduate programs. And so this is where you can see a listing of all of the programs that I counted when I did this, and we have the name of the university, the title of the program, and then a link to their website. And we do this for both the undergraduate and graduate programs. So if you want to go back and are looking for a program, or you have students that are looking for a program, this is a place to find that. I also wanted to show you the SIGHPC Education homepage. Aside from membership and our bylaws, the events page is something you can keep an eye on. This is where I have the presentation slides for today, the links to the events, and I will then post the links to the recorded YouTube videos once those are posted, and any other links to other events or sponsored workshops or other things that would be of use to members will be placed on these pages. So I just wanted to draw your attention to that. And with that, I'm going to go back to the Hangouts page if I can get there. And I'm going to stop screen sharing to avoid a headache here. And so now I'm going to ask Scott to come in and see if any questions have accumulated, and could you pose those questions, or if you haven't posted them yet, this is the time to do that. And so Scott, do we have any questions at this point?
The first question that came in from Ramses, you already referenced. He was asking, where is the list of programs available? And you just showed us that on the HBC University website.
Okay.
From Chris, the question is there data on enrollment in the undergraduate majors and minors in computational science?
There is no formal data. There have been intermittent surveys of those programs. The last one, I think, was done by University of Tennessee about 2 years ago, so the data are kind of old. I would say in general the enrollments are modest, and I think the reason that they're modest is that for all the reasons I mentioned earlier about recruiting students, marketing the programs, and so on. So they're surviving, but they haven't gone to great scale, and that's why there are too few students coming out of the pipeline that have these skills.
Okay, next from Ed, what programming language was used in Ohio State University's undergraduate minor in computational science?
In the simulation and modeling class, we actually used MATLAB for the introductory course, where we didn't let them use any toolboxes. We made them actually do programming concepts in MATLAB, and then they can take a follow-on course in programming that either involves Python, I think, or C. Those are some of the options that they have in that program.
That was the list of questions that have been posed so far.
Okay, I'm gonna pause for a minute or two and just to see if there's anything else as follow-up. While we're waiting for that, I might note that we're also looking for ideas on upcoming events. We have on our radar a couple of things. One is to do a similar overview of professional training and potential for certification for professionals. And that'll probably be the subject of our January meeting. We have some ideas for other activities, presentations, but we would appreciate receiving any ideas you have of presentations that you think would be useful, and you can post them here or send them by email to me. My email address is on the SIGHPC education page, and we certainly welcome your ideas and suggestions. Anything else come in, Scott?
Chris asked the question, have you seen specific marketing techniques that are effective at attracting students?
I worked with one community college on one of my projects, Start State College, that actually made a really nice video about what is computational science to show to their students. It was only modestly successful, and I think we have to think about doing more things like that, so that we get out information about how computational science is used in business and industry as well as in academic research so that people understand it better. I think just posting stuff on a website at the university along with course lists is very ineffective. And we want to take opportunities to do things like I think the Stark State faculty actually visited high schools and did presentations about computational science. So I think we have to get the community to be a lot more active to recruit students in various ways.
David posted a URL, www.computerscienceonline.org/degree-programs. I would encourage people to look at the Q&A session to get the URL if you didn't get that.
Okay, and we'll put a summary. If you can hold on to that link, I'll put a summary of that in the notes for the meeting as well so that people will get that. I think there were 1 or 2 links that were referred to in the previous session as well.
Robert posted this note. Wofford has at least anecdotal evidence that computational science, sorry, this moves about, that computational science has better demographics than computer science by itself. Could this be a focus of any new surveys?
That's a good question. Women in computer science is a big issue, as well as other underserved groups. I think there are a lot more people that are interested in solving problems, so the idea of computational science and modeling to solve a practical problem, I think, appeals more to students than programming, even though that's not just what you do in computer science, that's how students perceive it. So I think there's an opportunity there to market to a wider range of students to get a more diverse workforce in this area. So that's a really good point.
No other questions have been posted, but I'll ask one. What I hear frequently from faculty and students are, what are the career opportunities in computational science once you have those skills? Are there sources where you can find those opportunities?
There are some. They're not a huge number, but there's actually a couple of job boards where you can actually find, if you can do a Google search for computational science and you can actually find postings for that. On the HBC University page, we try to post job opportunities as well as internship opportunities. And if any of you have those kinds of opportunities, we'd be happy to get them posted there. We're trying to make that sort of a central resource for these kinds of things. It's very scattered at this time where those things are, and what we're trying to do is to at least find pointers to them at a central place. So there are some places to find those now if you look for them.
So another question I'll pose is, you pointed to a lot of the competency information. Are there courses that are available that teach some of these that we can look at and either use or modify?
There's a couple that we've done as part of the Exceed project, and a couple that Blue Waters is doing as collaborative online courses. So the Exceed ones you can find if you go to the exceed.org page and go under training. You can find a couple of courses full courses in parallel computing. These are full semester courses, as well as a bunch of other training materials. The Blue Waters stuff also I think we have links to that, the existing materials there in a couple of areas. We're offering a scientific visualization course, collaborative course in the spring, and an extreme scaling course there, and those materials will eventually be posted as well. I have examples of other syllabi and stuff like that that haven't been posted, but if anyone wants to see them, I'd be glad to share them. And I'm also collecting them, so if you have anything to share, I'd appreciate receiving those things as well.
You want to reference CSERD too?
Yeah, well, CSERD and the Computational Science Education Reference Test, which is also connected to the HBC University site, also indexes, both of those sites index computational science education materials. So either of those could be searched to find some other materials. So that's a good point, Scott.
And I apologize if I butcher the name, but Kieran has asked, how effective are online or remote training courses?
Really, teaching online is a whole different skill, and so how effective they are really depend on uh, how much extra help can be given to online students through some medium, whether that's through some interactive sessions or through help documents or help boards or something like that. So the online courses we teach often have a local faculty member that you can visit personally for help. Plus we have help sessions online. It's certainly a different way to teach and to learn than face to face, but you can do that very effectively.
David tried to post a question which is incomplete, so I'll read it and ask him to post more. The question is, how do you feel about websites like, and it stops. So either it didn't come through or something, but David, if you want to repost. Maybe that was the reference to the URL he posted previously.
Oh, okay, okay. So
Yeah.
the question is what then?
How do you feel about websites like, and he points to
Oh,
computerscienceonline.org/degree-programs. I'm
I mean, it
guessing.
really, there's no way to generalize about that, but it really depends whether it's giving you the information you need to get to. Um, so I think that some of those things can be quite useful because if somebody's trying to put together a course or a curriculum, if there are examples that they can find that are easily available, that can really shorten the time it takes them to put those materials together, as long as there's enough detail there to help them out. So I think those can be useful. It really depends on their content, so it's hard to generalize.
Ramses asks the question, high school outreach is great, but not really scalable. A Teach the Teachers program may help there. Do you know of any such programs?
Uh, There isn't very much now. I've actually been working with a colleague of mine at Ohio State to try to insert something about computational modeling into the science education curriculum. That's sort of in its infancy, and we're trying to market that to other colleges of education to see if we can make that happen. But there are not very many people in the education college that have this kind of expertise. So it's going to take a while to make that happen. But that's probably the best way to do it if we can manage it.
Um, the Q&A bounces around. I'm sorry.
It's all right.
David says, yes, they want to have my website point to them. I'm not sure I want to support them.
So I assume you mean it's okay, you don't mind posting stuff, but you don't want to spend a lot of time answering questions. And of course, that's a problem for anybody that shares materials. So, I still think if you can contribute something to a repository, at least to links to materials, that's still useful. I don't think you have to commit to answering a huge number of questions after that. I know that on some message boards you get people that, I'm teaching a course and so, can somebody prepare it for me, and so I don't have to do any work, and I don't answer those questions either. So.
David also says that this URL, supercomputingchallenge.org, is a computational science competition that also has a teacher component.
Oh, okay. So that's a good
I
one
think
to
that's out of
reference.
New Mexico.
Yeah. Yeah, there are several things like that, and I know at Ohio Supercomputer Center here we have a summer institute for high school students that we've had for more than 25 years, and we can proudly say that a number of those people are now doctorate level computational scientists, so it has had some impact. Well, Scott, if there's no other questions, I guess we can adjourn the session. I want to thank everybody for joining. I want you to look out for another session in January, probably focusing on professional development. And a reminder again, if you have suggestions, links, or anything else that's come up during this, please feel free to email those to me so that I make sure to get them on one of our reference sites. So thank you all for joining, and Scott, thank you for your help today. And
I suppose you want to ask people to suggest topics for future sessions as well.
right, and yes, future session topics are also welcome. So thank you again, and I hope to be in touch with all of those that have joined in the future.
Thanks, Steve.
Okay, have a good holiday, everybody.